We're back. We're going to drift through the nebulas, those vast clouds of gas and dust suspended in the darkness between stars. These are places where time moves slowly, where light takes thousands of years to travel from their glowing edges to reach our eyes, where the dance of gravity shapes structures larger than we can truly comprehend. There's something deeply calming about nebulas. They exist on timescales that make human concerns feel beautifully small. A nebula might spend millions of years simply existing, slowly gathering itself, slowly changing, slowly becoming something new. There's no rush in these cosmic clouds. There's only the patient accumulation of hydrogen atoms, the gradual pull of gravity, the gentle pressure of starlight. As we explore these celestial formations together, you don't need to remember every detail or hold onto every fact. Let the information wash over you. Let the images form in your mind and then dissolve. We're simply traveling through space, together, observing these distant, glowing structures, noting their presence, appreciating their existence. Some of what you hear might surprise you. Some might spark a moment of quiet wonder. But mostly, we're just here to observe, to listen, to drift. Nebulas come in different forms. Some glow with their own light, energized by nearby stars. Some reflect the light of stars embedded within them or nearby. Some appear dark, visible only because they block the light of brighter objects behind them. And some are the expanding remains of stars that have died, their outer layers spreading outward into space like ripples on an infinite pond. Tonight's journey will take us to several of these remarkable places. We'll visit the Orion Nebula, where stars are being born this very moment in processes that began long before humans walked the Earth. We'll see the towering pillars of creation, structures of gas and dust that stand light years tall. We'll observe the Helix Nebula, sometimes called the Eye of God, which shows us what our own sun might look like billions of years from now. We'll encounter the Horsehead Nebula, a dark silhouette against a sea of glowing hydrogen. And we'll explore the Crab Nebula, the expanding remains of a star whose death was witnessed by astronomers nearly 1,000 years ago. These are not just clouds of gas. They are the birthplaces and graveyards of stars. They are recycling centers where the materials of old stars become the building blocks of new ones. They are laboratories where the elements that make up planets and people are forged and distributed. They are, in a very real sense, where we come from. But you don't need to think about that too deeply right now. For tonight, they're simply beautiful, distant things that exist regardless of whether we observe them. They were here before us. They'll be here long after. And right now, in this moment, we're just taking a peaceful look at what they are and how they came to be. Let's begin our journey where many astronomers do, with one of the brightest and nearest stellar nurseries in our night sky. If you've ever looked up at the constellation Orion on a winter night, you've probably seen 3 bright stars in a row that form what we call Orion's belt. Just below that belt, hanging like a sword, there's a fuzzy patch of light visible even to the naked eye. That fuzzy patch is the Orion Nebula, and it's one of the most remarkable places in our cosmic neighborhood. The Orion Nebula sits approximately 1,344 light-years away from Earth. To put that in perspective, imagine that light, traveling at 186,000 miles per second, has been journeying toward us from that nebula for over 13 centuries. The light reaching your eyes tonight left the Orion Nebula around the time Charlemagne ruled much of Europe. And yet, in cosmic terms, 1,344 light-years is practically next door. It's close enough that we can study it in extraordinary detail. This nebula spans roughly 25 light-years across. Try to hold that dimension in your mind for a moment. 1 light-year is nearly 6 trillion miles. 25 light-years is a distance so vast that if you could somehow travel at the speed of light, it would take you 25 years just to cross from one side of the nebula to the other. And yet, from Earth, this enormous structure appears as just a small fuzzy patch, about twice the angular size of the full moon, as it appears in our sky. The Orion Nebula is what astronomers call an emission nebula, specifically an H2 region. The H stands for hydrogen, and the 2 indicates that the hydrogen atoms have been ionized, meaning they've lost their electrons. This happens because of the intense ultraviolet light pouring out from a cluster of very hot, very young stars embedded in the nebula's heart. At the center of the Orion Nebula lies a grouping of 4 particularly bright stars called the trapezium. These stars are massive, much more massive than our Sun, and they burn with incredible intensity. Their ultraviolet radiation floods the surrounding gas with energy, stripping electrons from hydrogen atoms and causing the nebula to glow with a characteristic reddish hue. In photographs, you can often see this red glow mixed with blues and greens from other elements like oxygen and sulfur, creating swirling patterns of color throughout the cloud. These trapezium stars are young, cosmically speaking. They formed only about 1 million to 2 million years ago from the same cloud of gas and dust that makes up the nebula itself. 1 million years might sound like a long time, but stars can live for billions or even tens of billions of years. In stellar terms, the trapezium stars are newborns, and they're still surrounded by the material from which they formed. The nebula isn't just home to the trapezium, though. Astronomers have identified approximately 700 young stars in just a small central region about 2.5 light-years wide. And they've detected over 150 protoplanetary disks, or proplyds, which are basically solar systems in the earliest stages of formation. Each of these disks is a swirling cloud of dust and gas orbiting a young star, and from these disks, planets will eventually form, just as our Earth and the other planets in our solar system formed around our young sun about 4.5 billion years ago. Think about that for a moment. Right now, in the Orion Nebula, planetary systems are assembling themselves. Dust grains are sticking together, forming pebbles, then boulders, then planetesimals, then planets. Somewhere in that glowing cloud, there might be a planet forming that will, billions of years from now, have oceans and continents, and perhaps even life. All of this is happening right now, has been happening for millions of years, and will continue, happening for millions more. The Orion Nebula has a mass of about 2,000 times that of our Sun. Most of that mass is hydrogen, with helium making up most of the rest, and trace amounts of heavier elements like carbon, nitrogen, oxygen, and iron mixed in. This material is spread out over those 25 light-years, making the nebula far less dense than any vacuum we could create here on Earth. Even though the nebula appears bright in photographs, you could pass right through most of it without encountering more than a handful of atoms per cubic centimeter. It's bright not because it's dense, but because it's so incredibly vast. The structure of the Orion Nebula is complex. It's not a simple spherical cloud, but rather a complex three-dimensional structure with dense pillars, hollow cavities, and expanding shells. The trapezium stars have carved out a cavity in the cloud, their intense radiation and stellar winds pushing gas outward and creating a roughly bowl-shaped region. The nebula is actually part of an even larger structure called the Orion Molecular Cloud Complex, which spans hundreds of light years and includes other famous objects like the Horsehead Nebula and Barnard's Loop. Within the Orion Nebula, star formation is an ongoing process. Dense knots of gas and dust, called Bok globules, dot the nebula's interior. These globules are collapsing under their own gravity, and some of them will eventually form stars. The process isn't quick by human standards. It takes roughly 1 million years or more for a collapsing cloud to gather enough material and heat up enough to ignite nuclear fusion in its core and become a true star. The nebula is also slowly dispersing. The stellar winds from the massive young stars are pushing gas outward, and over the next several million years, much of the nebula will be blown away. The stars will emerge from their birth cloud, fully formed and spreading out into the galaxy. Some will remain loosely bound together as an open cluster. Others will drift apart, each going their separate way through the Milky Way. Eventually, all that will remain of the Orion Nebula will be a scattering of stars, and perhaps some faint wisps of gas, the last remnants of a once glowing cloud. But that dispersal is still millions of years in the future. For now, the Orion Nebula continues to glow, continues to form stars, continues to exist as one of the most spectacular sights in our night sky. And because it's so close, because it's so bright, and because it's positioned in such a prominent constellation, it has been observed and studied by countless people throughout human history. Ancient peoples surely noticed it. Renaissance astronomers described it. Modern telescopes have revealed its secrets in stunning detail. The beauty of the Orion Nebula lies not just in its appearance, but in what it represents. It's a reminder that stars are not eternal, unchanging fixtures, but that they are born, live, and die. It shows us the process by which the universe creates new suns, new planets, new possibilities. And it does all of this with a patience and a grandeur that puts our daily lives into perspective. As you think about the Orion Nebula, imagine that vast cloud hanging in space, glowing softly with the light of young stars, slowly rotating, slowly changing, slowly creating. Imagine the density variations within it, the shock waves traveling through its gas, the magnetic fields threading through its structure. Imagine a protoplanetary disk, no larger than our solar system, spinning around a newborn star, the raw material for future planets, condensing grain by grain. And then let that image fade. Let it become just another piece of information, another fact about the universe, another reminder that space is full of wonders that exist whether we think about them or not. The Orion Nebula will still be there tomorrow night. It will still be forming stars. It will still be glowing. You don't have to. Hold on to it. You can just know that it's there, doing what it does, in its own time, at its own pace. About 7,000 light-years from Earth, in the constellation Serpens, there's a nebula called the Eagle Nebula, also known as Messier 16. This nebula spans about 70 by 55 light-years and is home to thousands of stars in various stages of formation. But the Eagle Nebula is famous for one particular feature, a feature so iconic that it has become one of the most recognizable images in all of astronomy: the Pillars of Creation. The Pillars of Creation are three towering columns of gas and dust, each several light-years tall. The tallest of these pillars stretches approximately 4 light-years from base to tip. 4 light-years. That's roughly the distance from our Sun to the nearest star system, Alpha Centauri, and then back halfway again. These aren't small structures, they are immense, cosmic-scale formations that dwarf anything we have in our solar system. The pillars are composed primarily of cool molecular hydrogen mixed with dust. The temperature within the densest parts of these pillars is only a few tens of degrees above absolute zero, making them some of the coldest places in our region of the galaxy. Despite their cold temperature, or perhaps because of it, these pillars are active regions of star formation. Young stars are being born inside the densest knots of gas within the pillars, hidden from view in visible light but detectable in infrared wavelengths. These structures were formed by a process called photoevaporation. The Eagle Nebula contains a cluster of massive, hot stars that formed earlier from the same cloud of gas and dust. These stars emit enormous amounts of ultraviolet radiation, which heats and ionizes the surrounding gas. This energetic radiation also exerts pressure on the gas, pushing it outward. The less dense regions of the nebula were pushed away first, leaving behind the denser regions where gravity holds the gas more tightly. Over time, this creates pillars and columns of relatively dense material standing against the flow of radiation and stellar wind. The process is somewhat like erosion, except instead of water carving rock, it's light and stellar wind carving gas and dust. The pillars point back toward the source of the radiation, their tips facing the hot stars that are sculpting them. At the very tips of the pillars, you can sometimes see small nodules or knots of particularly dense gas. These are called evaporating gaseous globules, or EGGs, and some of them contain forming stars. The pillars of creation are slowly being destroyed by the very radiation that makes them visible. The intense ultraviolet light from nearby stars is gradually evaporating the gas, causing the pillars to erode away. Estimates suggest that the pillars may only have another few million years before they are completely dispersed. In cosmic terms, this is a relatively short time. The pillars are a transient phenomenon, a temporary structure that exists for just a brief moment in the life of the galaxy. There's even some evidence to suggest that the pillars might have already been destroyed. Observations by the Spitzer Space Telescope in 2007 showed a cloud of hot dust near the pillars that could be the result of a shockwave from a supernova explosion. If this interpretation is correct, the supernova would have occurred about 6,000 years ago, and its shockwave would have reached the pillars about 1,000 years ago, potentially destroying them. However, because the pillars are 7,000 light-years away, we won't see this destruction for another 1,000 years. The light showing the pillars being destroyed hasn't reached us yet. So for now, from our perspective, the pillars still stand. This is one of the strange consequences of astronomy. We always see objects as they were in the past, not as they are now. When we look at the pillars of creation, we see them as they appeared 7,000 years ago, during the time when human civilization was just beginning to develop agriculture and build the first cities. We have no way of knowing their current state. For all we know, they might already be gone, dispersed into space, the stars within them scattered. But until the light showing that dispersal reaches us, the pillars remain, frozen in time in our observations. The image of the pillars of creation that most people know was captured by the Hubble Space Telescope in 1995. That image, showing the three dark pillars silhouetted against a sea of glowing gas with bright stars scattered throughout, became instantly iconic. It was revisited by Hubble in 2014 with newer, more sensitive cameras, revealing even more detail and creating an updated version that shows the intricate structure of the gas and the young stars embedded within. The James Webb Space Telescope has also observed the pillars of creation, using its infrared cameras to peer through the dust and reveal the stars forming inside. In Webb's view, the pillars appear more transparent, and the numerous young stars within and around them become visible as bright points of light. It's a reminder that what we see depends heavily on what wavelengths of light we observe. In visible light, the pillars are dark and opaque. In infrared light, they become translucent, revealing their hidden contents. The Eagle Nebula, which contains the pillars of creation, was discovered by the Swiss astronomer Jean-Philippe de Chazeau in 1745 or 1764. The records are somewhat unclear. It was later catalogued by Charles Messier in 1764, giving it the designation Messier 16. But it wasn't until the advent of modern astrophotography and space-based telescopes that the true beauty and complexity of the region became apparent. Similar pillar structures exist in other star-forming regions. The Carina Nebula, for instance, has its own set of pillars that have been dubbed the Pillars of Destruction because they are being eroded even more rapidly than those in the Eagle Nebula. The NGC 3603 region also contains pillar-like structures. It seems that wherever you have massive star formation in dense molecular clouds, you get these kinds of sculpted features. The pillars of creation have become more than just an astronomical object. They've become a cultural icon, a symbol of cosmic beauty and the power of modern astronomy. They've appeared on book covers, in documentaries, in art installations. They represent our ability to see and appreciate the distant structures of our universe, to understand the processes that shape them, and to marvel at their existence. But at their core, they're just gas and dust. Just hydrogen molecules and silicate grains and carbon compounds arranged by gravity and shaped by starlight. They don't know they're beautiful. They don't know they're famous. They simply exist, towering in the darkness, slowly birthing stars, slowly eroding away, operating on timescales that make human history seem like a brief flicker. As you imagine the pillars of creation, picture those vast columns rising up against a background of glowing pink and red gas. Picture the young stars at their tips, their light beginning to push back against the very clouds that formed them. Picture the knots of denser gas within the pillars, each one potentially a future solar system, with planets and moons and comets waiting to form. Picture the slow, inexorable process of erosion, the pillars gradually wearing away under the onslaught of stellar radiation. And then let that image settle. Let it become background. The pillars will continue their slow transformation whether you think about them or not. They'll continue forming stars, continue eroding, continue existing in their particular corner of the galaxy. You don't need to hold on to them. They're just there, doing what pillars of interstellar gas do, in their own time, at their own pace. When we look at photographs of nebulas, one of the first things we notice is their color. The Orion Nebula glows in shades of red and pink with hints of green and blue. The Horsehead Nebula appears as a dark brown or black silhouette against a vibrant red background. The Helix Nebula shows rings of red and blue with knots of various hues scattered throughout. These colors are not just aesthetically pleasing. They tell us about the chemical composition and physical conditions within these cosmic clouds. Nebulas glow because their gases are energized. In emission, nebulas, this energy typically comes from ultraviolet radiation emitted by hot young stars embedded within or near the cloud. These ultraviolet photons have enough energy to knock electrons out of atoms, a process called ionization. When those electrons eventually recombine with atoms, they release energy in the form of light at very specific wavelengths, and those specific wavelengths correspond to specific colors. Hydrogen is the most abundant element in the universe, making up about 75% of all ordinary matter. In nebulas, hydrogen is often the dominant component, sometimes comprising 90% or more of the gas. When hydrogen is ionized by ultraviolet light and then recombines, it emits light at several specific wavelengths. The strongest and most visible of these emissions is called hydrogen alpha, which occurs at a wavelength of 656.3 nanometers. This wavelength falls in the deep red part of the visible spectrum. This is why so many nebulas appear red in photographs. The hydrogen alpha emission is strong and distinctive, and it gives emission nebulas their characteristic reddish glow. However, hydrogen emits at other wavelengths too. Hydrogen beta, at 486 nanometers, produces a cyan or blue-green color. Hydrogen gamma, at 434 nanometers, appears blue. When all these emission lines are combined and there's minimal dust absorption, the overall color can appear more magenta or pink rather than pure red. Oxygen is another common element in nebulas, and it too has characteristic emission lines. Doubly ionized oxygen, written as O3, emits strongly at 500.7 nanometers, which appears as a vibrant blue-green or teal color. Singly ionized oxygen emits at other wavelengths. The presence of oxygen emission can significantly change the apparent color of a nebula. In regions with high oxygen content, like the core of the Orion Nebula, the combined light from hydrogen and oxygen can produce yellowish, greenish, or even bluish-white hues. Sulfur adds another layer to the color palette. Singly ionized sulfur, or S2, emits at wavelengths around 671 and 673 nanometers, which appears as a deep red, slightly different from the red of hydrogen alpha. Astrophotographers often use filters that isolate these specific wavelengths, hydrogen alpha, oxygen 3, and sulfur 2, and then assign them different colors in the final image to create what's called the Hubble palette. In the Hubble palette, sulfur is typically mapped to red, hydrogen to green, and oxygen to blue. This creates striking, colorful images that highlight the different chemical components of the nebula, though the colors in these images are not what you would see with your eyes. The natural color of a nebula, the color you would see if you could get close enough with eyes as sensitive as a camera, depends on several factors: the chemical composition of the gas, the intensity and spectrum of the ionizing radiation, the amount and distribution of dust, and the relative strengths of different emission lines. In general, emission nebulas with minimal dust tend to appear pink or magenta due to the combination of red hydrogen alpha and blue hydrogen beta and hydrogen gamma emissions. As dust increases, the blue light gets scattered or absorbed more than the red light, shifting the color toward deeper red and orange tones. Dust itself doesn't emit much visible light, but it does two important things: it scatters light and it absorbs light. Small dust grains, smaller than the wavelength of visible light, scatter blue light more efficiently than red light. This is the same reason our daytime sky is blue and sunsets are red. The dust scatters blue light away, allowing red light to pass through. In regions with thick dust, this can make nebulas appear redder than they would otherwise. Dust can also glow in the infrared if it's warm enough. Starlight heats the dust grains and they re-radiate that energy at longer wavelengths. This infrared glow is invisible to our eyes but can be detected by infrared telescopes. In images that combine visible and infrared data, the warm dust often appears as orange or yellow hues. Reflection. Nebulas have a different color story. These nebulas don't emit their own light, but instead reflect the light from nearby stars. The color of a reflection nebula depends on the color of the illuminating star and the scattering properties of the dust. Blue stars illuminate dust that appears blue in reflection because the small dust grains scatter blue light more efficiently. This is similar to why distant mountains can appear blue. The famous Pleiades cluster, the Seven Sisters, is surrounded by a faint blue reflection nebula. Dark nebulas, like the Horsehead, don't emit significant light and don't reflect much light. They're visible only as dark patches or silhouettes against brighter backgrounds. Their apparent color is really just the absence of light, though in images they often appear brown or reddish-brown due to the very faint scattering and emission from the sparse gas and dust at their edges. The colors in nebula images are often enhanced or modified to bring out details or to highlight different components. A pure scientific image might map different wavelengths to different colors in ways that don't match natural vision. An aesthetic image might boost saturation to make colors more vivid. A composite image might combine data from multiple telescopes observing at different wavelengths, from radio to X-ray, each represented by an arbitrary color. But beneath all the processing and enhancement, there are real photons with real wavelengths, emitted by real atoms undergoing real physical processes. The red glow of hydrogen alpha is genuine, even if the camera and processing enhance it. The greenish tint of oxygen emission is real, even if it's mapped to a different color in a false color image. The colors tell us about temperatures, densities, velocities, chemical abundances. They are a language, a way that the universe communicates its properties to us across vast distances. When you look at a colorful nebula image, you're seeing a translation. The original message is in the form of photons arriving at Earth after journeys of hundreds or thousands of years through space. Those photons are sorted by wavelength, measured, counted, and then translated into an image on a screen or print. The colors might not be exactly what your eye would see if you were there, but they represent something real. The specific wavelengths of light emitted by specific atoms in specific physical conditions. There's a certain poetry to this. The reddish glow you see in an image of the Orion Nebula is the visible signature of electrons dropping from higher to lower energy levels in hydrogen atoms. Each photon represents a single atomic event, and when you see a glowing region, you're seeing trillions upon trillions of these events happening simultaneously. The colors are quantum mechanics made visible, atomic physics on a cosmic scale. As you think about the colors of nebulas, let the specific details fade. You don't need to remember the exact wavelength of hydrogen alpha or the chemical symbol for doubly ionized oxygen. Just know that nebulas glow, that their glow tells us what they're made of, and that the beautiful colors in images represent real physical processes. The universe is not just bright or dark. It's full of specific hues and tints that reveal its composition and conditions. And with that understanding settling quietly in the background, we can move on to another type of nebula, one that shows us the future fate of stars like our Sun. About 655 light-years from Earth, in the constellation Aquarius, floats a structure that has been called the Eye of God, though it has no particular divine significance. This structure is the Helix Nebula, and it represents the fate that awaits our Sun and billions of other stars like it. The Helix Nebula is a planetary nebula, though the name is misleading. Planetary nebulas have nothing to do with planets. The name comes from the 18th century when astronomers, looking through small telescopes, saw these objects as round, disc-like shapes that resembled planets. We now know they are something quite different. The outer layers of dying stars, expelled into space and glowing in the light of the remaining stellar core. The Helix Nebula formed when a star similar to our Sun reached the end of its normal life. For most of a star's existence, it fuses hydrogen into helium in its core, and this fusion reaction produces the energy that makes the star shine and provides the outward pressure that counteracts gravity. But eventually, after billions of years, the hydrogen in the core runs out. For our Sun, this will happen in about 5 billion years. For the star that created the Helix Nebula, it happened about 10,600 years ago. When the core hydrogen is exhausted, the core contracts and heats up. This causes the outer layers of the star to expand enormously, and the star becomes what's called a red giant. Our Sun will eventually expand so much that it might reach out past the orbit of Mars, engulfing Mercury and Venus and possibly Earth in the process. These outer layers are cool compared to the star's core, which is why the star appears red. During this red giant phase, the star becomes unstable. It pulsates, swelling and contracting. Strong stellar winds blow off the outer layers, shedding mass into space at a gentle pace. This process can last for hundreds of thousands or even millions of years, and it creates a slowly expanding shell of gas around the star. Eventually, the outer layers drift away completely, revealing the hot core of the star. This core, now called a white dwarf, is incredibly dense. It packs a mass similar to our Sun's into a volume about the size of Earth. A teaspoon of white dwarf material would weigh as much as several elephants if you could somehow bring it to Earth. The white dwarf is also extremely hot, with surface temperatures that can reach 100,000 degrees Celsius or more. The intense ultraviolet radiation from this hot white dwarf ionizes the surrounding shell of gas that was previously expelled. The gas begins to glow, and a planetary nebula is born. The Helix Nebula is this glowing shell, illuminated from within by its central white dwarf. The Helix Nebula spans about 2.5 to just under 3 light-years across, though its outer, fainter regions extend even farther. Despite its size, it appears relatively small in our sky, about half the angular diameter of the full moon. This is because of its distance. If it were closer, it would be one of the most spectacular objects in the night sky. As it is, it requires a telescope or good binoculars to see clearly, though under very dark skies, a careful observer might glimpse it as a faint, round patch. The structure of the Helix Nebula is complex. It's not a simple sphere, but rather has a shape more like a prolate spheroid, essentially a 3-dimensional ellipse, with its major axis tilted between 21 and 37 degrees from our line of sight. This gives it a distinctive appearance, somewhat like looking at a tube or helix from an angle, which is where the name comes from. One of the most intriguing features of the Helix Nebula is the presence of thousands of small, knot-like structures embedded in its glowing gas. These are called cometary knots because they have small, bright heads and long, faint tails, somewhat resembling comets. Each knot is about the size of our entire solar system. There are estimated to be around 20,000 of these knots in the Helix Nebula. The origin of these cometary knots is still not fully understood. They might be denser clumps in the original stellar wind that survived the ionization process, or they might have formed when the fast wind from the hot white dwarf ran into the slower, previously expelled material, creating dense pockets. The tails point away from the central star, shaped by the ongoing stellar wind and radiation pressure. The central white dwarf itself is only about the size of Earth, but has a mass of about 93% that of our Sun. It's a cooling ember, no longer producing energy through fusion. Over trillions of years, far longer than the current age of the universe, this white dwarf will slowly radiate away its heat and eventually become a black dwarf, a dark, cold sphere of degenerate matter. But that final stage is so far in the future that no white dwarfs in the universe have had time to cool down completely yet. The Helix Nebula is expanding. Its inner regions are spreading outward at about 31 kilometers per second, and its outer regions at about 40 kilometers per second. Over time, this gas will spread thinner and thinner, eventually merging with the general interstellar medium. The nebula's glow will fade as it expands, and the central white dwarf cools. In 100,000 years or so, the Helix Nebula might be barely visible, a faint, enormous shell of gas surrounding a cooling stellar remnant. There's evidence that the central white dwarf in the Helix Nebula might be orbited by a planet. Recent observations have detected periodic variations in the white dwarf's light that could be caused by a planet passing in front of it. This planet, if it exists, would be about 2.3 times the radius of Earth and would have survived the star's red giant phase, though it would have been thoroughly scorched in the process. Alternatively, these variations might be caused by intrinsic stellar variability or other phenomena. The observations remain unconfirmed and represent an area of ongoing research. When we look at the Helix Nebula, we're looking at a preview of our own solar system's far future. In about 5 billion years, our Sun will begin its transformation into a red giant. The inner planets will be lost. The outer planets might survive, but will be altered beyond recognition. And eventually, our Sun will shed its outer layers and create its own planetary nebula, perhaps similar to the Helix. Any observers in distant star systems looking back toward our solar system in that distant era would see a glowing ring or sphere of gas surrounding a brilliant white dwarf. They might see cometary knots. They might photograph the structure and give it a name. And they would be looking at the scattered atoms that once composed the Sun, along with perhaps some atoms that once made up Earth and everything on it. This is not a tragedy. It's simply the life cycle of medium-sized stars. Every planetary nebula represents the same process. A star that lived for billions of years, steadily fusing hydrogen, providing light and warmth to any orbiting planets, eventually running out of fuel and returning its material to space. The carbon, nitrogen, oxygen, and other heavier elements forged in the star's interior are released into the interstellar medium, where they can be incorporated into new stars and planets. The Helix Nebula is not alone. There are hundreds of known planetary nebulas in our galaxy, and likely billions more too distant or too faint for us to see. Each one represents a star that has reached the end of its main sequence life. Some are round like the Helix. Others are elongated or bipolar, with lobes extending in opposite directions. Still others have complex multiple shell structures. The shape of a planetary nebula depends on many factors, including the star's rotation, whether it had a companion star, the presence of magnetic fields, and the timing of mass loss episodes. The Cat's Eye Nebula, for instance, shows a remarkable series of concentric shells, suggesting multiple episodes of mass loss over time. The Ring Nebula in Lyra appears almost perfectly circular from our viewpoint, though it's actually more cylindrical. The Dumbbell Nebula has a distinctive hourglass or apple core shape. Each one is unique, yet all follow the same basic pattern: an aging star shedding its outer layers. As you imagine the Helix Nebula, picture that enormous eye gazing out into space. Picture the hot white dwarf at its center, blazing with ultraviolet light. Picture the cometary knots scattered throughout the glowing gas, each one a dense pocket of matter caught in the stellar wind. Picture the slow expansion, the gradual fading, the inevitable dispersal of the nebula into the vastness of space. And then let that image settle. The Helix Nebula will continue its expansion, will continue to fade, will continue existing in its particular way for thousands of years to come before it finally dissipates. It doesn't require your attention. It's simply there, a waypoint in the life cycle of stars, a glimpse of futures both distant and inevitable. Not all nebulas glow. Some appear dark, visible only because they block the light from stars or glowing gas clouds behind them. These dark nebulas, or absorption nebulas, are among the coldest and densest regions in the galaxy, and they play a crucial role in star formation. The most famous dark nebula is probably the Horsehead Nebula, known formally as Barnard 33. It's located in the constellation Orion, about 1,500 light-years from Earth, making it relatively nearby in cosmic terms. The Horsehead is part of the same vast cloud complex that includes the Orion Nebula, the enormous Orion molecular cloud that spans hundreds of light-years. The Horsehead Nebula appears as a dark silhouette shaped remarkably like a horse's head and neck, set against the bright emission Nebula IC434. The shape is a coincidence, a particular configuration of dust and gas that happens to resemble a familiar form. From other angles or with different background illumination, it would appear completely different. But from our viewpoint here on Earth, the illusion is striking. The Horsehead extends about 3.5 light-years from top to bottom. The head itself is about half a light-year in height. These dimensions are smaller than some of the other structures we've discussed, but still vast by human standards. The nebula is composed of thick, cold dust and molecular gas, primarily hydrogen molecules, rather than the ionized hydrogen found in bright emission nebulas. The temperature within the Horsehead is low, around -260 degrees Celsius, or about 13 degrees above absolute zero. At these temperatures, atoms and molecules move very slowly, and the gas is extremely dense by interstellar standards, though still far less dense than any laboratory vacuum. This combination of cold temperature and relatively high density makes dark nebulas ideal places for star formation. Within the Horsehead Nebula, gravity is slowly pulling the gas and dust together. Over time, regions of higher density attract more material, growing denser still. Eventually, when a region becomes dense enough and the pressure and temperature at its core rise high enough, nuclear fusion ignites and a new star is born. Infrared observations of the Horsehead have revealed several young stars embedded within its dark form, invisible in ordinary light but glowing brightly in the infrared. The Horsehead is being slowly eroded by radiation from Sigma Orionis, a bright star system located off to the side. The ultraviolet light from these massive stars heats the surface of the Horsehead, causing atoms and molecules at the surface to evaporate away. This is why the edges of the Horsehead appear slightly fuzzy or irregular in detailed images. The nebula is being worn away molecule by molecule. Eventually, in about 5 million years, the Horsehead will be completely dispersed, its distinctive shape lost forever. But for now, it endures. The Horsehead has probably looked roughly the same for thousands of years from our perspective, though on cosmic timescales it's an ephemeral structure, it's a dark patch, a shadow, a place where starlight cannot penetrate, set against a background of glowing pink hydrogen. Dark nebulas exist throughout the galaxy. Some are famous, like the Coalsack Nebula, visible from the southern hemisphere, which appears as a prominent dark patch in the Milky Way. Others are catalogued in surveys like the Barnard Catalog, which lists hundreds of dark nebulas and dense dust clouds. These features can be small, just a light year or two across, or they can be enormous molecular cloud complexes spanning hundreds of light years. The Pipe Nebula, for instance, is a complex of dark nebulas near the galactic center that resembles a smoking pipe when seen in wide-field images. The Snake Nebula in Ophiuchus appears as a long, dark filament stretching across a field of stars. The Cone Nebula in Monoceros is a dark pillar, similar in some ways to the pillars of creation, but appearing as a silhouette rather than a glowing structure. Dark nebulas are crucial to our understanding of star formation. The denser regions of these clouds are where stars form, and by studying the distribution, temperature, and chemistry of dark nebulas, astronomers can learn about the conditions necessary for star birth. Radio telescopes can detect the faint emission from molecules like carbon monoxide within these clouds, mapping their structure and motion, even though they're invisible to optical telescopes. One of the interesting things about dark nebulas is that they're not truly dark. If you could fly a spacecraft into the Horsehead Nebula and look around, you wouldn't find yourself in pitch blackness. Light from distant stars would still filter through, though dimmed and reddened by the dust. The environment would be gloomy, like a very thick, dark fog, but not completely lightless. The darkness we see is a contrast effect. Compared to the bright, glowing gas behind it, the Horsehead appears dark to us, but it's still receiving some light from the surrounding stars. The dust in dark nebulas is composed of tiny, solid grains, typically a fraction of a micrometer in size, smaller than the wavelength of visible light. These grains are made mostly of carbon and silicates, rocky materials similar to sand but incredibly fine. The grains form when atoms in the outer layers of cool stars condense into solids, much like water vapor condensing into snowflakes, though at much higher temperatures. These dust grains are then expelled into space by stellar winds and incorporated into the interstellar medium. When light from distant stars passes through a dark nebula, the dust grains scatter and absorb some of that light. Blue light, with its shorter wavelength, is scattered and absorbed more efficiently than red light. This is why stars seen through dust appear redder than they would otherwise, a phenomenon called interstellar reddening. It's also why dark nebulas appear dark. They block a significant fraction of the light that would otherwise reach us from background stars. In many star-forming regions, dark nebulas and bright emission nebulas exist side by side. The bright nebulas are regions where hot, massive stars have already formed and are ionizing the surrounding gas, making it glow. The dark nebulas are regions where stars are still forming, or where the gas is too far from ionizing sources to glow. Often, you'll see intricate structures where glowing filaments weave around dark patches, creating complex three-dimensional sculptures of light and shadow. The Horsehead Nebula sits at the edge of a large molecular cloud. Behind it, from our perspective, is the glowing emission Nebula IC434, ionized by hot stars in the region. In front of it, or rather between us and it, is mostly empty space with a scattering of foreground stars. The Horsehead is oriented such that its neck points roughly toward us, with the muzzle of the horse pointing upward in most images. This orientation is, of course, a matter of chance. The nebula itself has no preferred direction. As you picture the Horsehead Nebula, imagine that dark silhouette suspended in space, cold and dense, slowly collapsing under its own gravity in some regions while being eroded away in others. Imagine the young stars hidden within it, glowing in infrared light. Imagine the background of red hydrogen emission, the bright stars scattered around it, the vast molecular cloud of which it's just a small, visible part, and then let the image become quiet. The horsehead will continue its slow existence, forming stars, eroding away, existing as a shadow for a few more million years before it's gone. It doesn't need your focus, it's just another structure in the galaxy, another place where gas and dust gather and transform. On July 4 in the year 1054 CE, Chinese astronomers recorded the appearance of a guest star in the constellation that we now call Taurus. This guest star was so bright that it was visible during the daytime for 23 days and remained visible at night for nearly 2 years. Japanese, Arabic, and Native American observers also recorded this event. They were witnessing a supernova, the catastrophic explosion of a massive star, and the expanding debris from that explosion is what we now call the Crab Nebula. The Crab Nebula, catalogued as Messier 1 because it was the first object in Charles Messier's famous catalogue of fuzzy objects that might be confused with comets, lies about 6,500 light-years from Earth. The light from the supernova explosion took 6,500 years to reach Earth, arriving in the year 1054. That means the actual explosion occurred about 7,554 years ago, in the time when early human civilizations were developing agriculture and building the first settlements. The nebula is now about 11 light-years across and still expanding at roughly 1,500 kilometers per second, or about 0.5% of the speed of light. At that rate, the outer edge of the nebula is moving outward at about 4,700 billion kilometers per year. Over the nearly 1,000 years since the light from the explosion reached Earth, the nebula has expanded considerably, though of course we've only been able to observe and measure that expansion for the last few centuries. The star that exploded was a massive star, probably between 8 and 12 times the mass of our Sun. It had lived its relatively brief life, fusing hydrogen into helium, then helium into carbon and oxygen, then those into heavier elements like neon, magnesium, silicon, and eventually iron. Each stage of fusion produced less energy and lasted for a shorter time. The final silicon-burning stage, which produces iron, lasted only a few days. When iron accumulated in the star's core, fusion stopped. Iron cannot be fused into heavier elements and release energy. Instead, fusing iron requires energy input. Without fusion to provide outward pressure to counteract gravity, the core collapsed catastrophically. In less than a second, a core the size of a planet collapsed to a sphere only about 20 kilometers across. The collapse released an enormous amount of gravitational potential energy, and the infalling outer layers of the star bounced off the incredibly dense core and were blown outward in a tremendous explosion. This explosion, the supernova, released as much energy in a few seconds as our Sun will release over its entire 10 billion year lifetime. Most of that energy was carried away by neutrinos, ghostly particles that barely interact with matter, but enough energy remained to heat and accelerate the star's outer layers to tremendous velocities, creating an expanding shell of hot gas and a brilliant flash of light visible across tens of millions of light-years. At the center of the Crab Nebula, hidden within the expanding gas, is the remnant of that collapsed core, a neutron star. This object is about 20 kilometers in diameter, but contains about 1.4 times the mass of our entire Sun. It's composed almost entirely of neutrons packed together at nuclear density. A teaspoon of neutron star material would have a mass of about 1 billion tons. This particular neutron star is also a pulsar, meaning it emits beams of radiation from its magnetic poles, and those beams sweep across space like a lighthouse beacon as the star rotates. The Crab pulsar rotates 30 times per second, and each rotation we detect a pulse of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. This pulsar was the first pulsar to be identified with a supernova remnant and one of the first pulsars discovered at all back in 1968. The pulsar is incredibly powerful. It emits about 100,000 times more energy than our Sun, despite being only 20 kilometers across. This energy comes from the pulsar's rotational energy. As it spins and emits radiation, it gradually slows down, though the slowdown is tiny, only about 38 nanoseconds per day. Over thousands of years, the pulsar will continue to slow, and eventually, millions or billions of years from now, it will spin so slowly that it will no longer emit detectable beams, becoming what's called a dead pulsar. The energy from the pulsar powers the nebula itself. The pulsar drives a powerful wind of high-energy particles into the surrounding gas, heating it and causing it to glow. This creates a region around the pulsar called a pulsar wind nebula, which appears in X-ray and infrared images as a torus and jet structure. The interaction between the pulsar wind and the expanding supernova debris creates the complex filamentary structures visible in optical images of the Crab Nebula. In visible light, the Crab Nebula appears as an oval or elliptical cloud of gas with a complex network of filaments running through it. These filaments are the remains of the star's outer layers, still hot and glowing, still expanding outward. The filaments are rich in elements like helium, carbon, oxygen, nitrogen, and iron, elements that were forged in the star's core and scattered into space by the explosion. The Crab Nebula has been observed continuously by astronomers since its discovery as a nebula in 1731 by John Bevis, though it wasn't connected to the supernova of 1054 until much later. Time-lapse images spanning decades show visible changes in the nebula's structure as it continues to expand, and as the filaments shift and change due to instabilities in the expanding gas. The nebula emits radiation across the entire electromagnetic spectrum. In radio waves, it's one of the brightest objects in the sky. In X-rays, the pulsar and pulsar wind nebula shine brilliantly. In gamma rays, it's a powerful source. This makes it a favorite target for astronomers studying high-energy astrophysics and the behavior of matter under extreme conditions. Other supernova remnants exist throughout the galaxy. Some, like Cassiopeia A, are even younger than the Crab. Others, like the Vela supernova remnant, are much older and more dispersed. Each one tells a story of a massive star reaching the end of its life and returning its material to the interstellar medium. The heavy elements produced in the star and in the explosion itself are now part of the gas spreading through space, available to be incorporated into new stars, new planets, and potentially new life. When you consider that almost every element heavier than helium in your body was produced inside stars and scattered by supernova explosions, nebulas like the Crab take on additional significance. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these were forged in stellar cores and distributed by explosions like the one that created the Crab Nebula. In a very real sense, we are made of stardust, and supernova remnants are the proof of that connection. As you think about the Crab Nebula, imagine that expanding cloud of gas and debris glowing in the energy from the central pulsar. Imagine the filaments, each one a stream of atoms moving at high speed through space. Imagine the pulsar itself, spinning 30 times per second, emitting beams of radiation that sweep across the galaxy. Imagine the Chinese astronomers in 1054 looking up at a new star that had appeared in the sky, not knowing they were witnessing an explosion that occurred millennia before their civilization existed, and then let that image settle into the background. The Crab Nebula continues its expansion, continues its slow dispersal into the interstellar medium. The pulsar continues its spin, though slowing imperceptibly. The nebula will persist for tens of thousands of years more before it becomes too faint and dispersed to see. You don't need to hold on to it. It's simply another object in the galaxy, another waypoint in the life cycle of stars. One of the most striking things about nebulas, once you start to grasp the scales involved, is how slowly they change. We're accustomed to change happening on human timescales, seconds, days, years, but nebulas operate on timescales of thousands, millions, even billions of years. They remind us that the universe is patient in ways we can barely comprehend. Consider the Orion Nebula. Star formation there has been ongoing for at least the past 1 million years. The youngest stars are less than 1 million years old. Some regions might be forming stars right now, but right now is a relative term. The nebula is 1,344 light-years away, so what we see as right now is actually what was happening 1,344 years ago. And star formation itself is not a quick process. A collapsing cloud of gas takes roughly 1 million years or more to accumulate enough material and heat up enough to ignite fusion and become a star. This means that if you could somehow watch the Orion Nebula with perfect time-lapse photography, speeding up time so that 1 million years passed in 1 second, you would see clouds of gas slowly gathering, growing denser, heating up, and eventually igniting as stars appeared throughout the nebula. You'd see some massive stars live their brief lives and explode as supernovas, their shock waves triggering new rounds of star formation in nearby gas. You'd see the nebula slowly evolving, changing shape, some regions dispersing as others collapse. But we don't have that perspective. We see a single snapshot, frozen in time by the finite speed of light. The Orion Nebula looks largely the same in photographs taken decades apart because decades are nothing on these timescales. Even centuries make little difference. The nebula looked the same when Galileo first turned a telescope toward Orion as it does now, 400 years later. It will look much the same 400 years from now. The pillars of creation have likely changed somewhat in the 7,000 years since the light we now see left them. The pillars are being eroded at a pace of a few tens of kilometers per second. In 7,000 years, the erosion would have removed several trillion kilometers of material, a significant amount. But the pillars are light years in extent, and even removing trillions of kilometers wouldn't dramatically change their overall appearance. They're being worn away slowly, steadily, inexorably, but still slowly. Planetary nebulas like the helix expand noticeably over human timescales, at least in principle. The helix is expanding at about 30 to 40 kilometers per second, which means it grows by roughly 1 trillion kilometers per year, or about 6,700 times the Earth-Sun distance. Over a human lifetime of 80 years, it would expand by 80 trillion kilometers. That sounds like a lot, but the nebula is nearly 3 light-years across, or about 30 trillion kilometers. So even after a human lifetime, the expansion would only increase the nebula's size by a fraction of a percent, barely noticeable even with precise measurements. The Crab Nebula is one of the few nebulas that changes noticeably over human timescales. It's expanding at about 1,500 kilometers per second, which is quite fast. Over a century, the nebula grows by about half a light year. Astronomers comparing images taken decades apart can see visible changes in the structure and position of filaments. This is unusual, though. Most nebulas change far too slowly for us to notice directly. The slow pace of change in nebulas is a consequence of their low density and enormous size. Even though gas in the Orion Nebula might be moving at tens of kilometers per second, it takes a long time for that gas to travel across the light years of space within the nebula. Even though the pillars of creation are being eroded, the amount of material being removed each year is tiny compared to the total mass of the pillars. This slow pace means that nebulas exist in a kind of suspended animation from our perspective. They're not static, gas is moving, temperatures are changing, stars are forming and dying, radiation is ionizing atoms. But all of this happens so slowly, spread over such vast volumes, that we perceive nebulas as essentially unchanging objects. This is also true of star formation itself. The process by which a cold cloud of gas collapses and forms a star takes about 1 million years for a star like our Sun, and longer for smaller stars. During that time, the cloud heats up very gradually. The central density increases slowly. Eventually, the temperature and density at the core reach a point where fusion begins, but this is a gradual ignition, not a sudden event. The star slowly settles into a stable state where fusion energy balances gravitational contraction. Once a star forms, it enters its main sequence phase, where it will spend the vast majority of its life. For a star like our Sun, this phase lasts about 10 billion years. 10 billion years. That's more than twice the current age of the Earth. It's longer than multicellular life has existed on our planet. It's so long that the universe itself was less than 4 billion years old when our Sun formed. Massive stars live shorter lives, but even they exist for millions of years. A star 20 times the mass of our Sun might live for only 10 million years before it explodes as a supernova. 10 million years is still an incredibly long time by human standards. Civilization, as we know it, is perhaps 10,000 years old. 10 million years is 1,000 times longer than recorded human history. Nebulas teach us about patience and perspective. They show us that the universe operates on timescales that dwarf human experience. The structures we see are not eternal, but they're so long-lived compared to us that they might as well be. The Orion Nebula will still be forming stars millions of years from now. The Helix Nebula will still be expanding for tens of thousands of years. The Crab Nebula will continue glowing for millennia to come. This perspective can be humbling, but it can also be calming. Our daily concerns, our urgent problems, the things that keep us awake at night, all of these exist on human timescales. On cosmic timescales, they're ephemeral, flickering moments. The nebulas don't care about our deadlines or our worries. They simply exist, slowly changing, operating according to the laws of physics, indifferent to our presence. There's a certain peace in that indifference. The universe will continue whether we observe it or not. Stars will form, live, and die. Gas will collapse and disperse. Elements will be forged and scattered. And all of this will happen on timescales so vast that our entire species is just a brief chapter in a story that spans billions of years. When you think about the timescales involved with nebulas, let the specific numbers fade away. You don't need to remember exactly how long it takes for a star to form or how fast the Crab Nebula is expanding. Just hold on to the general idea. Nebulas change slowly, exist for long periods, and operate on timescales that make human experience seem brief. They are patient structures in a patient universe. We've mentioned distances and sizes throughout this journey, numbers like 1500 light-years or 25 light-years across. But it's worth pausing to really consider what these measurements mean and how impossibly vast these structures truly are. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, or 186,000 miles per second. In 1 second, light travels far enough to circle the Earth nearly 7.5 times. In 1 year, traveling at that incredible speed, light covers about 9.5 trillion kilometers, or nearly 6 trillion miles. That's a light year. The nearest star system to us, Alpha Centauri, is about 4.4 light-years away. If you could travel at the speed of light, which nothing with mass can do, it would take you 4.4 years to get there. With current technology, it would take tens of thousands of years. 4.4 light-years is so far that the fastest spacecraft humans have ever built, the Voyager probes, traveling at roughly 17 kilometers per second, would take about 75,000 years to cover that distance. The Orion Nebula is 1,344 light-years away. That's more than 300 times farther than Alpha Centauri. If Alpha Centauri seems unreachably distant, the Orion Nebula is in a completely different category of remoteness. And yet, cosmically speaking, it's nearby. Most objects in our galaxy are thousands or tens of thousands of light-years away. Other galaxies are millions or billions of light-years distant. The Andromeda Galaxy, the nearest large galaxy to our Milky Way, is about 2.5 million light-years away. The light we see from Andromeda left that galaxy 2.5 million years ago, during the time when early humans were just beginning to use stone tools. The most distant objects we can observe are over 13 billion light-years away. Their light has been traveling toward us for most of the age of the universe. Now consider the size of a nebula. The Orion Nebula spans about 25 light-years. That means if you were somehow at one edge of the nebula and could shine a flashlight, it would take 25 years for that light to reach the opposite edge. The nebula is so large that light itself needs decades to cross it. Our entire solar system, from the Sun to the orbit of Neptune, is about 60 times the Earth-Sun distance across, or about 60 astronomical units. That's roughly 8.9 billion kilometers. Light takes about 8 hours to travel, from the Sun to Neptune. The Orion Nebula is 25 light-years across. It would take roughly 27,000 solar systems laid side by side to span the diameter of the Orion Nebula. And the Orion Nebula is not particularly large as nebulas go. The Carina Nebula is about 300 light-years across. Some molecular clouds span thousands of light-years. The scale becomes almost meaningless because we have nothing in our everyday experience to compare it to. Within these vast nebulas, the density is incredibly low. A typical emission nebula might have a few hundred to a few thousand atoms per cubic centimeter. That sounds like a lot until you realize that the air you're breathing has about 25 billion trillion molecules per cubic centimeter. The best laboratory vacuum we can create still has millions of atoms per cubic centimeter. The interior of a nebula is emptier than any vacuum we can produce on Earth. Yet, because nebulas are so enormous, they contain tremendous amounts of material. The Orion Nebula has a mass about 2,000 times that of our Sun, despite being almost entirely empty space. It's the volume that makes the difference. When you integrate over light-years of space, even a very low density adds up to substantial mass. Flying through a nebula would not be like flying through a cloud here on Earth. You wouldn't see your visibility drop. You wouldn't encounter turbulence or moisture. You'd simply be in space, with perhaps a slightly higher density of atoms around you, not enough to notice. The beautiful glowing structures we see in images appear that way because we're looking through many light years of faintly glowing gas. The integration of that faint light along our line of sight creates the luminous appearance. From inside the nebula, each point would emit only a tiny amount of light, barely detectable. This is one of the strange things about nebulas. They appear bright and substantial in images, but an observer inside, one would perceive only the faintest of glows in any direction. It's like the difference between looking at fog from a distance, where it appears as a distinct cloud, versus being inside the fog, where you just see reduced visibility and a grayness all around. The scale of nebulas also means that events within them unfold slowly. A shock wave from a supernova, traveling at thousands of kilometers per second, still takes thousands of years to cross a large nebula. Gas falling toward a forming star, even falling at tens of kilometers per second under gravity, takes hundreds of thousands of years to accumulate. The light from a star in the nebula takes years to reach the far edges of the surrounding gas. There's no center or edge in the sense we usually think of them. A nebula doesn't have a sharp boundary. It gradually fades into the surrounding interstellar medium. Where exactly does the Orion Nebula end and regular space begin? There's no clear answer. It's a gradual transition from slightly denser to slightly less dense gas, from glowing gas to gas that's too faint to see. When we quote a size for a nebula, we're usually referring to the region bright enough to be easily visible in images or where the density is above some threshold. But fainter gas related to the nebula might extend much farther. The Orion Nebula is part of the much larger Orion Molecular Cloud Complex, which spans hundreds of light years. Where one structure ends and another begins is often a matter of definition and convenience. Distances in space are measured using various methods. For relatively nearby objects, astronomers can use parallax, the apparent shift in position of an object when viewed from different locations. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. The amount of shift tells us the distance. This method works well out to a few thousand light years, which is why we have good distance measurements for nebulas like the Orion Nebula. For more distant objects, astronomers use other techniques, like comparing the observed brightness of stars to their known intrinsic brightness, or measuring the redshift of light, which indicates how much the universe has expanded since the light was emitted. Each method has its uncertainties, and distance measurements in astronomy often come with error bars of 10% or more. Still, even with uncertainties, the distances to nebulas are staggering. The Horsehead Nebula at 1500 light-years, the Helix at 655 light-years, the Crab at 6500 light-years. These are distances that we cannot physically traverse with current or foreseeable technology. We can only observe these objects from afar, collecting the light that has traveled for centuries or millennia to reach us. And yet, that observation connects us to these distant places. When you look at an image of the Orion Nebula, the photons hitting your eyes or your camera sensor are photons that were emitted by atoms in that nebula over 1,000 years ago. They traveled across the galaxy, across the immense emptiness between stars, and arrived here, carrying information about that distant place. In that sense, looking at nebulas is a form of time travel. We see them not as they are now, but as they were when the light left them. As you consider the scale of nebulas, let the specific numbers blur. Don't worry about remembering exactly how many light years across the Orion Nebula is, or precisely how far away the Crab Nebula sits. Just understand that these are objects of almost incomprehensible size, sitting at almost incomprehensible distances, yet we can see them, study them, understand them. The universe is vast beyond measure, but it's not beyond our ability to observe and appreciate. Nebulas are not just beautiful or interesting structures. They are essential components of galactic ecology, serving as the recycling centers of the universe. They are where old stars return their material and where new stars and planets form from that returned material. They close the circle of stellar life and death. When the universe began about 13.8 billion years ago in the event we call the Big Bang, it contained only the simplest elements: hydrogen, helium, and trace amounts of lithium. That was all. Every other element, everything heavier than lithium, has been created since then inside stars or in stellar explosions. Stars create heavier elements through nuclear fusion. In their cores, stars fuse light elements into heavier ones, converting hydrogen into helium during the main sequence of their lives, then helium into carbon and oxygen, and in the most massive stars, continuing through neon, magnesium, silicon, and eventually iron. This process, called nucleosynthesis, is how virtually every element heavier than lithium came to exist in the universe. The fusion process releases energy, which is why stars shine. 4 hydrogen nuclei can fuse together through a series of steps to form one helium nucleus. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into it. That missing mass has been converted into energy according to Einstein's famous equation E equals mc squared. The energy released keeps the star hot and provides the outward pressure that prevents the star from collapsing under its own gravity. For most of a star's life, it fuses hydrogen into helium. Our Sun has been doing this for about 4.5 billion years and will continue for another 5 billion years or so. But eventually, the hydrogen in the core runs out. When that happens, the core contracts and heats up, while the outer layers expand. The star becomes a red giant. If the core gets hot enough, about 100 million degrees Celsius, helium can begin to fuse into carbon through a process called the triple alpha process. 3 helium nuclei, each, consisting of 2 protons and 2 neutrons, combine to form one carbon nucleus. In stars more massive than our Sun, the process continues. Carbon can fuse with helium to form oxygen. Further fusion creates neon, magnesium, silicon, sulfur, and eventually iron and nickel. Each successive stage of fusion requires higher temperatures and pressures, and each stage produces less energy and lasts for a shorter time. A massive star might spend millions of years fusing hydrogen, hundreds of thousands of years fusing helium, hundreds of years fusing carbon, and only a few days fusing silicon into iron. Iron is the end of the line for fusion energy production. Fusing iron into heavier elements requires energy input rather than releasing energy. So when a massive star's core fills with iron, fusion stops. Without fusion energy to support it, the core collapses catastrophically in less than a second, and the star explodes as a supernova. The explosion creates temperatures and pressures high, enough to forge elements heavier than iron through rapid neutron capture, a process called the R process. Gold, platinum, uranium, and other heavy elements are created this way, either in supernova or in the collisions of neutron stars. All these elements, from carbon to uranium, are ejected into space when stars die. Low-mass stars like our Sun shed their outer layers gently, creating planetary nebulas. Massive stars explode as supernovae, violently dispersing their material. Either way, The elements created in the stars are returned to the interstellar medium, the vast, thin gas that fills the space between stars. The interstellar medium is composed mostly of hydrogen and helium left over from the Big Bang, but it also contains all the heavier elements created and dispersed by previous generations of stars. About 90% of the atoms in the interstellar medium are hydrogen, with most of the remainder being helium and less than 1% consisting of heavier elements. That 1% might seem small, but it's crucial. It includes all the carbon, nitrogen, oxygen, silicon, iron, and other elements that make up planets and people. The interstellar medium is not uniformly distributed. Density varies from as low as 100 ions per cubic meter in hot, diffuse regions to about 1 trillion molecules per cubic meter in dense molecular clouds. Even the densest regions are far more rarefied than the best vacuum we can create in a laboratory. For comparison, the air we breathe contains about 25 billion trillion molecules per cubic centimeter, while the average density in the interstellar medium is roughly 1 atom per cubic centimeter. Despite its low density, the interstellar medium contains a substantial amount of mass. About 15% of the visible matter in the Milky Way is in the form of interstellar gas and dust. Over the immense volumes of space between stars, even a very low density adds up to billions of solar masses of material. This material is the raw material for new stars and planets. Nebulas, particularly the dense molecular clouds, are where the interstellar medium concentrates enough to begin the process of star formation. Gravity pulls the gas together. As it collapses, it heats up. Eventually, if enough mass accumulates and the temperature and pressure rise high enough, nuclear fusion ignites and a new star is born. That new star contains the elements from previous stars. The carbon in its core, the oxygen in any planets that form around it, the iron that might someday form a planet's core, all of these came from earlier stars that died and returned their material to space. Each generation of stars enriches the interstellar medium with more heavy elements. The first stars, formed from the nearly pure hydrogen and helium of the early universe, contained almost no heavy elements. Modern stars, like our Sun, contain about 2% heavy elements by mass. Stars forming today in regions of active star formation might contain even more. This is the cosmic cycle of matter. Stars are born from nebulas, which are concentrations of the interstellar medium. Stars live, fusing light elements into heavier ones. Stars die, returning their material to the interstellar medium. The enriched interstellar medium forms new nebulas. New stars form from those nebulas, and the cycle continues. Nebulas are the visible part of this cycle. They are places where the interstellar medium has gathered, where old material from dead stars mixes with primordial hydrogen and helium. They are where new stars form from the ashes of old ones. They are recycling centers, taking the output of stellar death and transforming it into the input for stellar birth. When you look at a nebula, you're seeing this process in action. The gas glowing in an emission nebula contains elements forged in previous stars. The dark dust in an absorption nebula includes carbon grains that condensed in the atmospheres of red giants. The young stars forming in a stellar nursery are built from material that was once part of other stars, perhaps stars that exploded billions of years ago. The elements in your body followed this same path. The oxygen you breathe, the carbon in your DNA, the calcium in your bones, the iron in your blood, all of these were created inside stars that lived and died before our sun was born. Those stars returned their material to the interstellar medium. That material became part of a nebula, perhaps a nebula much like the Orion Nebula. That nebula collapsed under its own gravity and formed the Sun and the planets, including Earth. And here you are, made of atoms that were forged in the cores of long-dead stars and recycled through nebulas billions of years ago. This connection is not poetic exaggeration. It's literal fact. The atoms in your body have been through this cycle. They've been part of stars, part of nebulas, part of planets, and now they're part of you. Eventually, after you die and after the Earth itself is destroyed when the Sun becomes a red giant, those atoms will return to space, perhaps to become part of a new nebula, and eventually part of new stars and new planets. Nebulas are where this happens. They are the intermediaries between stellar death and stellar birth. They are the cosmic compost heaps, breaking down the material from dead stars and preparing it for new life. They operate on timescales that make human life seem infinitesimally brief, but they connect us directly to the long history of matter in the universe. As you think about nebulas as recyclers, let the specific chemical details fade. You don't need to remember which elements are produced at which stages of stellar evolution or the exact density of the interstellar medium. Just understand that nebulas are part of a cycle, that they connect the death of old stars to the birth of new ones, and that this cycle is what gave rise to the elements that make up everything we see around us, including ourselves. And with that understanding settling quietly into place, we can turn our attention to a few more nebulas, each with their own quiet stories to tell. If you look toward the constellation Sagittarius on a summer night, particularly if you're viewing from the southern hemisphere or from mid-northern latitudes during the summer months, you'll find a region rich with nebulas and star clusters. Two of the most prominent objects in this region are the Lagoon Nebula and the Trifid Nebula, close neighbors in space and in our sky. The Lagoon Nebula, catalogued as Messier 8, sits approximately 4,000 to 6,000 light-years from Earth. The distance estimates vary somewhat depending on the measurement method used, which is common for objects at these distances. The nebula spans about 110 light-years by 50 light-years, making it considerably larger than the Orion Nebula. Despite this size and its distance, the Lagoon Nebula is one of only two star-forming nebulas visible to the naked eye from mid-northern latitudes. The other, of course, is the Orion Nebula. The lagoon gets its name from a dark lane of dust that runs through its center, creating the appearance of a lagoon or bay when viewed through a telescope. This dark lane is composed of thick dust that blocks the light from the glowing gas behind it, similar to how the dark nebulas we discussed earlier appear as silhouettes. On either side of this dark lane, the nebula glows with the characteristic reddish-pink color of ionized hydrogen. At the heart of the lagoon, nebula lies an open cluster of young stars called NGC 6530. These stars formed from the same cloud of gas and dust that makes up the nebula, and the most massive among them are now ionizing the surrounding gas, causing it to glow. Two particularly bright stars, numbered 7 and 9 Sagittarii, are primarily responsible for energizing the nebula. These are massive, hot stars that pour enormous amounts of ultraviolet radiation into the surrounding gas. The Lagoon Nebula contains several Bok globules, those dense, dark knots of gas and dust where stars are currently forming. It's an active stellar nursery, with star formation happening right now in multiple locations throughout its structure. The globules are slowly collapsing under their own gravity, and over the next million years or so, they will likely produce new stars that will add to the population already present. The nebula appears quite large in our sky, spanning about 90 by 40 arc minutes. For reference, the full moon appears about 30 arc minutes across, so the Lagoon Nebula covers an area roughly 3 times the width of the moon and slightly larger than its height. This makes it an excellent target for amateur astronomers with binoculars or small telescopes. Under dark skies, even with the naked eye, you can see it as a faint, elongated glow. Just above the Lagoon Nebula in the sky, separated by only about 2 degrees, sits the Trifid Nebula, catalogued as Messier 20. The Trifid is smaller and more distant than the Lagoon, sitting approximately 5,000 light-years from Earth. Its name, meaning divided into 3 lobes, comes from the dark dust lanes that appear to split the nebula into 3 distinct sections when viewed through a telescope. What makes the Trifid particularly interesting is that it's actually 3 types of nebula in one. The central region is an emission nebula, glowing red from ionized hydrogen, just like the Lagoon and the Orion Nebula. Surrounding the emission nebula, particularly toward the upper portion, is a blue reflection nebula where light from young stars is being scattered by dust grains. And running through the emission nebula are the dark lanes, dark nebulas composed of thick dust that blocks the light from the glowing gas behind them. This combination of emission, reflection, and dark nebula, all in one relatively small structure, makes the Trifid a fascinating object to study. It shows us different aspects of the star formation process happening side by side. The emission nebula indicates regions where massive stars have already formed and are ionizing the gas. The reflection nebula shows where starlight is illuminating dust without ionizing it, typically around slightly less massive or younger stars. And the dark lanes are the densest regions of the cloud, where the next generation of stars might form. At the center of the emission portion of the Trifid sits HD 164492A, a massive star more than 20 times the mass of our Sun. This O-type star is the primary source of the ultraviolet radiation that ionizes the surrounding gas. It's surrounded by a cluster of approximately 3,100 young stars, most of them less than a few million years old. The Hubble Space Telescope has captured detailed images of a stellar jet in the Trifid Nebula, a narrow stream of gas, being ejected from a young star deep within a dense cloud. This jet is about 3/4 of a light-year long and points directly away from the massive central star. Such jets are common features of star formation, representing material that's being expelled along the rotation axis of a forming star, though we don't fully understand all the details of how they're produced and collimated. The Trifid Nebula appears much smaller in the sky than the Lagoon, spanning only about 20 to 28 arc minutes. Still, this makes it visible in binoculars under dark skies, appearing as a faint, fuzzy patch just above the much brighter Lagoon. Through a telescope, the dark lanes become visible, giving the nebula its characteristic Trifid appearance. Both the Lagoon and the Trifid were discovered in the 18th century. The Lagoon was discovered by Giovanni Hodierna in 1654, making it one of the earliest nebulas to be recorded. Charles Messier catalogued it in 1764. The Trifid was discovered by Messier himself on June 5, 1764, during the same sweep of the sky that revealed many other deep sky objects. These 2 nebulas, sitting close together in our sky and at roughly similar distances in space, offer a convenient comparison. The Lagoon is large, bright, and relatively nearby, showing us a massive star-forming complex with numerous young stars and active star birth. The Trifid is smaller and slightly more distant, but it packs multiple types of nebula into one compact package, showing us different stages and aspects of the star formation process in a single object. When you imagine these nebulas, picture them suspended in the same general region of the galaxy, both in the constellation Sagittarius, both glowing with the light of young stars, both actively forming new stars even as we observe them. Picture the dark lane cutting through the lagoon, the three lobes of the trifid, the young star clusters embedded in both structures. And then let those images settle. The lagoon and trifid will continue their slow evolution, forming stars, dispersing gas, existing in their particular corner of the Milky Way. They don't require your attention. They're simply there, two more examples of the star formation process that happens throughout the galaxy in their own time, at their own pace. There's something almost geometric about the Ring Nebula. Catalogued as Messier 57, it appears in telescopes as a nearly perfect ring or donut of glowing gas suspended in space. This precision of form has made it one of the most recognizable and frequently observed planetary nebulas in the sky. The Ring Nebula sits approximately 2,000 light-years from Earth in the constellation Lyra, though distance estimates have varied over the years from as low as 1,400 light-years to as high as 5,000 light-years. The current best estimate places it around 2,000 to 2,500 light-years away. It's relatively close in cosmic terms, close enough that we can study it in great detail with modern telescopes. The nebula itself is about 1 light-year in diameter, though its fainter outer regions extend somewhat farther. This makes it considerably smaller than the Helix Nebula, which we discussed earlier. Despite its smaller size, the Ring Nebula appears reasonably bright in telescopes, with an apparent magnitude of 8.8. This puts it just beyond the limit of naked eye visibility, but easily visible in binoculars or a small telescope. The Ring Nebula formed when a star similar to our Sun exhausted its hydrogen fuel and entered the red giant phase. Over time, this red giant star shed its outer layers in a series of gentle pulsations and stellar winds. When the hot core was finally exposed, it began ionizing the surrounding shell of gas, causing it to glow. The nebula has been expanding for approximately 1,610 years, give or take 240 years based on observations of its expansion rate. The central star of the Ring Nebula is a white dwarf with a surface temperature of approximately 125,000 degrees Celsius, making it one of the hottest stellar objects in our region of the galaxy. This extreme temperature is what allows it to emit the intense ultraviolet radiation needed to ionize the surrounding gas and make the nebula glow. The white dwarf has a mass of about 0.61 to 0.62 solar masses, typical for white dwarfs, and it's slowly cooling over time. For many years, astronomers thought the Ring Nebula was simply a ring or spherical shell of gas. However, detailed observations by the Hubble Space Telescope revealed a more complex structure. The nebula is actually shaped more like a prolate spheroid or football, with its long axis oriented roughly toward us. What appears as the ring is actually the thicker equatorial region of this football-shaped structure, while the central region appears darker because we're looking through less dense gas along the polar axis. Think of it like looking down the length of a barrel. The sides of the barrel appear bright because you're looking through more material, while the center appears darker because you're looking through empty space. The Ring Nebula works the same way. We happen to be viewing it from a direction that's close to one of its poles, so we see a ring shape. If we could view it from the side, it would look more elongated, similar to other planetary nebulas like the Dumbbell Nebula. The colors of the Ring Nebula tell us about its composition and the conditions within it. The inner region appears blue-green due to emission from doubly ionized oxygen at wavelengths around 495 and 500 nanometers. These are the so-called forbidden lines that occur only in regions of very low density. The outer regions show a reddish hue from hydrogen emission at 656 nanometers, the hydrogen alpha line we've discussed before, along with contributions from ionized nitrogen. One of the fascinating features of the Ring Nebula is the intricate structure visible in high-resolution images. The inner rim of the ring shows dark, irregular knots of dense gas that the stellar winds from the central star haven't yet been able to blow away. These knots are probably similar to the cometary knots seen in the Helix Nebula, dense pockets of material that are more resistant to ionization and erosion. The nebula also has a faint outer halo that extends well beyond the bright inner ring. This halo is material that was ejected earlier in the star's evolution, before the final shedding that created the bright inner ring. The halo is elongated along the nebula's major axis and shows a knotty, irregular structure. Observations suggest that both the inner ring and the outer halo originated from slow winds during the star's asymptotic, giant branch phase before it shed its outer layers completely. Recent observations using advanced instruments have revealed even more surprises. In 2025, astronomers using a powerful spectrograph detected an unexpected elongated structure of ionized iron inside the Ring Nebula, something that had never been seen before. This iron bar sits in the middle of the familiar ring and was completely unknown until these very detailed observations revealed it. The origin of this iron feature is still being investigated. It might reveal something new about how the star expelled its outer layers, showing that the process was more complex than previously thought. Alternatively, and more intriguingly, the iron might be an arc of plasma resulting from the vaporization of a rocky planet that was caught up in the star's expansion during its red giant phase. If a planet had orbited close to the star, it could have been engulfed and destroyed as the star expanded, with the vaporized material now appearing as this iron-rich structure. This remains unconfirmed speculation, but it demonstrates how even well-studied objects like the Ring Nebula can still hold surprises. The Ring Nebula is expanding at about 20 to 30 kilometers per second. Photographic observations over a period of 50 years show the rate of expansion is roughly 1 arc-second per century. This is slow enough that you wouldn't notice any change even if you observed it repeatedly over a human lifetime, but fast enough that precise measurements can detect it over decades. The nebula is approaching us at about 21 kilometers per second, part of the general motion of objects in our region of the galaxy. This approach velocity has nothing to do with the nebula's expansion. It's simply the overall motion of the system through space relative to our solar system. The Ring Nebula was discovered by the French astronomer Antoine Darquier de Pellepoix in January 1779. Charles Messier independently discovered it shortly afterward and catalogued it as the 57th object in his famous catalogue. The central white dwarf star was discovered much later, in September 1886, by the Hungarian astronomer Gino Gothard, who photographed the nebula and found the faint star at its center. The Ring Nebula is easy to find in the night sky. It sits about 40% of the way from the star Beta Lyrae to Gamma Lyrae, two of the brightest stars in the constellation Lyra. This position, combined with its reasonable brightness, makes it a favorite target for amateur astronomers. Through a small telescope, it appears as a faint, grayish ring or oval. Larger telescopes reveal more detail, showing the darker central region and hints of structure in the ring. Long exposure photographs, or CCD imaging, brings out the colors and the faint outer halo. As you imagine the Ring Nebula, picture that nearly perfect ring of glowing gas, the blue-green inner region and reddish outer zone, the hot white dwarf at the center blazing with ultraviolet light. Picture the football-shaped structure oriented toward us, giving us this distinctive ring-like view. Picture the slow expansion, the gradual fading that will occur over the next tens of thousands of years, and then let that image become quiet. The Ring Nebula will continue its expansion, will continue to fade, will continue existing in its particular form for thousands of years before it disperses completely. It doesn't need your focus. It's just another planetary nebula, another dying star returning its material to space, another structure operating according to physical laws on cosmic timescales. With these additional nebulas settling into the background alongside the others we've visited, we can now shift our attention to how we observe these distant structures from our vantage point here on Earth. For most of human history, nebulas were nearly invisible. Ancient. Astronomers could see a few fuzzy patches in the night sky, places where there seemed to be faint, cloudy light instead of sharp points of stars. The Orion Nebula, for instance, was likely observed by ancient peoples, though it wasn't clearly recorded until the early 17th century. The Andromeda Galaxy appeared as a faint smudge, but without telescopes, there was no way to see the detail or understand what these objects truly were. The invention of the telescope changed everything. In 1610, Nicolas Claude Fabry de Peiresc observed the Orion Nebula through a telescope and described it as a cloudy region. Over the following centuries, as telescopes improved, more nebulas were discovered and catalogued. Charles Messier, a French astronomer searching for comets in the 18th century, compiled a catalogue of fuzzy objects that might be confused with comets. His catalogue included many nebulas, and objects are still referred to by their Messier numbers today. The Crab Nebula is M1. The Orion Nebula is M42. The Ring Nebula is M57. In the 19th century, the development of spectroscopy allowed astronomers to analyze the light from nebulas and determine their composition. William Huggins, in 1864, turned his spectroscope toward a planetary nebula and discovered that it showed emission lines rather than the continuous spectrum of starlight. This proved that nebulas were made of glowing gas, not vast collections of unresolved stars as some had thought. Photography transformed nebula observation in the late 19th and early 20th centuries. Long photographic exposures could capture far more detail and fainter structures than the human eye could see through a telescope. Images of the Orion Nebula, the Andromeda Galaxy, and other objects revealed beautiful, complex structures that had been invisible or barely visible before. The 20th century brought increasingly powerful telescopes and new ways of observing. Radio telescopes, developed in the 1930s and 40s, could detect radio waves emitted by neutral hydrogen and molecules in cold molecular clouds. This allowed astronomers to map the distribution of gas throughout the galaxy, even in regions where dust blocked visible light. Infrared telescopes could see through dust and detect the warm glow of forming stars embedded in nebulas. X-ray telescopes could observe the high-energy emissions from supernova remnants and pulsar wind nebulas. Space-based observatories revolutionized the field. The Hubble Space Telescope, launched in 1990, provided unprecedented views of nebulas in visible and ultraviolet light, free from the blurring effects of Earth's atmosphere. Hubble's images of the pillars of creation, the Helix Nebula, the Crab Nebula, and countless other objects became iconic, showing the beauty and complexity of these structures in stunning detail. Other space telescopes added more capabilities. The Spitzer Space Telescope, observed in the infrared, revealing warm dust and young stars. The Chandra X-ray Observatory captured the high-energy emissions from supernova remnants and active galactic nuclei. More recently, the James Webb Space Telescope, with its large mirror and sensitive infrared instruments, has provided even deeper and clearer views, peering through dust to reveal the hearts of star-forming regions. From Earth, with the naked eye, only a handful of nebulas are visible under dark skies. The Orion Nebula appears as a fuzzy patch in Orion's sword. The Andromeda Galaxy, which is technically a galaxy but appears nebulous to the unaided eye, can be seen as a faint, elongated smudge. The Pleiades star cluster is surrounded by a faint reflection nebula visible under very dark conditions. Beyond these, you need optical aid. Binoculars or a small telescope can reveal many more nebulas. The Ring. Nebula in Lyra, the Dumbbell Nebula in Vulpecula, the Lagoon Nebula, and the Trifid Nebula in Sagittarius. All of these become visible with modest equipment under reasonably dark skies. They don't appear as the colorful, detailed structures seen in photographs. Instead, they show up as faint, grayish patches or rings. The human eye is not very sensitive to color at low light levels, so nebulas appear mostly monochrome when viewed visually. Larger amateur telescopes can reveal more detail and fainter nebulas. With a telescope of 8 to 12 inches in aperture, under dark skies, you can see structure in the Orion Nebula, detect the dark lane in the Trifid Nebula, and glimpse faint planetary nebulas and supernova remnants. But even then, the view doesn't match the photographs. Photographs can integrate light over minutes or hours, revealing far fainter structures and bringing out colors. The eye sees only what light falls on it in an instant. Astrophotography has become increasingly accessible to amateurs. With modern cameras, tracking mounts, and image processing software, dedicated, amateur astronomers can produce images of nebulas that rival those from professional observatories decades ago. Long exposures capture faint details. Filters can isolate specific wavelengths, like hydrogen alpha, to enhance contrast. Stacking multiple images reduces noise. The result is stunning views of celestial structures that would be invisible to the eye alone. Professional observatories operate telescopes far larger and more sophisticated than anything available to amateurs. The Keck telescopes in Hawaii, with mirrors 10 meters across, can collect enormous amounts of light. The Very Large Telescope in Chile combines 4 8.2-meter telescopes for even greater light-gathering power. These instruments, combined with adaptive optics to compensate for atmospheric turbulence, produce images nearly as sharp as those from space-based telescopes. Radio telescope arrays, like the Very Large Array in New Mexico or the Atacama Large Millimeter Array in Chile, map the distribution of molecules and cold gas in molecular clouds. These observations reveal the dense cores where stars are forming, the velocity structure of the gas, and the presence of complex organic molecules in space. Infrared observatories, both ground-based and space-based, peer through dust to see the young stars embedded in their birth clouds. Observing nebulas isn't just about taking pictures. It's about understanding the physical processes at work. Spectroscopy reveals the chemical composition, temperature, density, and velocity of the gas. Photometry measures the brightness at different wavelengths, allowing astronomers to determine the energy output and the type of radiation being emitted. Polarimetry measures the polarization of light, which can reveal information about magnetic fields and dust grain alignment. Multi-wavelength observations combine data from different parts of the electromagnetic spectrum to build a complete picture. A nebula might be bright, invisible. Light due to ionized hydrogen, bright in infrared due to warm dust, bright in radio due to molecules, and bright in X-rays due to a central pulsar or shock wave. Each wavelength reveals a different aspect of the physics at work. Combining them provides a comprehensive understanding. Nebulas are also observed over time. Time domain astronomy tracks how objects change. Supernova remnants expand, and comparing images taken years or decades apart reveals the expansion rate. The shapes of planetary nebulas evolve as the central star heats up and as the ejected gas continues to spread outward. Variable stars within emission nebulas brighten and fade, changing the illumination of their surroundings. The observation of nebulas has taught us much of what we know about stellar evolution, star formation, the interstellar medium, and the chemical evolution of galaxies. Every new instrument, every new wavelength, every improvement in sensitivity or resolution reveals something previously unknown. There's still much to learn. The exact mechanisms of star formation, the details of how planetary nebulas form and evolve, the structure and evolution of supernova remnants, all of these remain active areas of research. But beyond the science, there's simple wonder. Looking at an image of the Orion Nebula, or the Helix Nebula, or the Pillars of Creation, knowing that these are real places, real structures made of real atoms following real physical laws, is profoundly moving. These aren't paintings or artistic renderings. They're photographs of actual objects, sitting out there in space, glowing and changing and existing, whether we look at them or not. When you see an image of a nebula, you're seeing light that has traveled for hundreds or thousands of years across space. You're seeing photons that were emitted by atoms in a distant cloud, photons that have crossed the galaxy to reach Earth, to pass through a telescope or camera, and to form an image. You're connecting, through light, to a structure vastly larger than anything on Earth, operating on timescales far longer than human history, existing in a realm we can never physically visit but can observe and study and appreciate from afar. As you think about observing nebulas, let the technical details recede. You don't need to remember the diameters of telescope mirrors or the specific wavelengths of emission lines. Just understand that nebulas can be observed, that we have many ways of studying them, and that each observation adds to our understanding of these remarkable structures. They're out there, glowing and changing, whether we look or not, but our observations bring them into our awareness and allow us to appreciate their existence. And that brings us to the end of our journey through the nebulas, to a moment of quiet reflection on what we've seen. We've traveled through several nebulas together tonight, observing their structures, understanding their processes, considering their scales and timescales. We've visited the Orion Nebula, where stars are being born among glowing clouds of hydrogen. We've seen the Pillars of Creation, towering columns of gas slowly eroding under the light of nearby stars. We've learned about the colors that nebulas display and what those colors tell us about their composition. We've observed the Helix Nebula, a preview of our sun's distant future. We've encountered the dark silhouette of the Horsehead Nebula, a cold cloud where stars form in darkness. We've examined the Crab Nebula, the expanding remains of a star that exploded nearly 1,000 years ago. We've considered the timescales on which nebulas operate, the millions of years it takes for stars to form, the slow erosion of pillars, the gradual expansion of planetary nebulas. We've thought about scale, about light years and the vast distances and dimensions involved, about how empty space really is, even where it appears bright and full. We've explored the role of nebulas as cosmic recyclers, taking the material from dead stars and preparing it for new generations of stars and planets. And we've touched on how these distant structures are observed, how light from them crosses space to reach our telescopes and cameras, allowing us to see and study objects we can never visit. Nebulas are patient. They exist on timescales that make our lives seem brief, our concerns ephemeral. They operate according to physical laws that care nothing for human affairs. They are beautiful, but their beauty is incidental. They're simply structures of gas and dust, shaped by gravity and starlight, following the same principles of physics that govern everything else in the universe. There's something calming about that. The universe continues its slow unfolding regardless of our participation. Stars form, live, die. Gas collapses and disperses. Elements are created and scattered. The cycle continues, as it has for billions of years, as it will for billions more. You don't need to remember everything we've discussed. The specific numbers, the names of objects, the details of processes, all of these can fade. What remains is the general understanding. Nebulas are vast clouds of gas and dust, birthplaces and graveyards of stars, structures that connect the cosmic past to the cosmic future, operating on scales of space and time that dwarf human experience. They're out there right now. The Orion Nebula is forming stars. The pillars of creation are slowly eroding. The Helix Nebula is expanding. The Crab Nebula's pulsar is spinning. All of this is happening whether you think about it or not, whether anyone thinks about it or not. And perhaps that's the most peaceful thought of all. The universe doesn't require our attention. It simply exists, vast and ancient and patient, full of structures like nebulas that have been here far longer than we have and will remain far longer than we will. You can rest now, knowing that out there in the darkness between stars, nebulas glow quietly, slowly changing, connecting the deaths of old stars to the births of new ones, recycling the elements that make up everything we know, operating on timescales that make our brief lives seem like single heartbeats in the long life of the cosmos. Thank you for joining me on this journey through the nebulas. If you enjoyed this quiet exploration of the universe, I'd be grateful if you'd consider liking this video and subscribing to Nebula Nights. There are more cosmic journeys to come, more peaceful explorations of the structures and processes that make up our universe. Until next time, rest well, and remember that the stars and nebulas will still be there tomorrow night, and the night after, patiently existing in the vast darkness of space.